All right, good evening, everybody. I have a couple of questions here that you guys have asked already. So let's see. We'll get started with homework number 11. Number 6. Okay, now I am a little short on time, so I probably can only be here about an hour, more or less. So I'm not going to be able to go through all of this problem. But I will tell you how to. It is pretty involved, just the whole process of it. But let's see. Let's try to get through as much as we can, right? I'll at least set you up onto how to do something like this. All right. Now, when we read through this problem here, okay. All right. So one thing to notice here is so number 6, they give me a matrix A. And 1, 6, 2, 1, 0, 7. Okay, so, and they tell me that this is the matrix for the transformation R4 to R3 with respect to these bases. So A is actually the transformation matrix relative to B and B prime. Okay, so what does that mean? That means then, and they give us those matrices, they're right there in front of us. So what does that mean in terms of, for part A, when it asks me to find T of V1 relative to basis B prime? All right. Okay, so what that means here is that we actually already know it's already here in the matrix here. So there's actually no work involved here, right? If this is already relative to these bases, then the matrix of the transformation matrix for V1 is this column vector here, right? So this is actually 3, 1, negative 3. Okay, and then and so forth, right? T of V2, B prime would be the second column vector here, right? The image there. So that would be negative 2, 6, 0. Okay, and again, how do we know that? We know that because they tell us already that that matrix A is with respect to those bases. Okay, so and then V3 would be the third column, and then V4 would be the T of V4 relative to B prime would be the fourth column there. Okay, any questions on that part? All right, no questions. So I'm assuming that we're okay with that. Okay, so then it's already given to me. The images, they tell me that this is true. So the image is just the columns of those vectors. All right, because remember, how is this matrix generated? It's generated by taking an augmented matrix and so forth, right? So I got that from the given information. The matrix is already relative to those bases. Okay, and so forth. You would do that for V3 and V2, V3, V1, V2, V3, and V4. Then the column vectors represent the images relative to B prime. Okay. All right. Um, I'm not sure your notation, Eugene. Again, here, what I'm basing this on is that they already give me the transformation matrix. Right? So we're given this, and we're told that this is relative to B and B prime. Okay, so what that means is that they took the transformation of the vector v1 and then they wrote that in terms of the column vector. So again, remember these vectors are coefficients for the bases, in this case b prime. Okay, so the difference, so let's answer that question, right, Lindsay? So what is the difference between this and this? Okay, so the difference here is that when we look at t of v1, 3, 1, negative 3, this is a column vector that is representing the coefficients relative to the basis b prime, right? So in terms, how do I find t of v1? Well, I'm going to take this, and again, right, these are coefficients relative to b prime. So what I'll do is, this is 3 times w1 plus 3, or excuse me, 1 times w2 minus 3 times w3. All right. And then I will do this calculation to find what t of v1 is. Right? This only gives you the coefficients relative to matrix B prime. This, you want the actual vector in R3, and you find it in this way. So you would do that to all four of those, right? So you essentially take that column and do this calculation, right? So here, let me move on to another one here, right? So what you would have here is you would have, in order to find, so that was t of v1. So if you wanted to find t of v2, right? Again, that's relative to matrix, excuse me, to basis b prime, and this is a column vector of coefficients. If you wanted to actually find here, if we wanted to find t of v2, right, the way we would do that, we would take these right, and those will be my coefficients for the w1, w2, w3. Okay? So that's how you would work your way through A and B, right? The matrix gives you those columns, give you the coefficients. To find the transformation vectors, you would use those coefficients relative to that matrix B prime. Okay? Does that make sense? We're okay with part A and B? Okay. All right. Now, for C, when we have to find a formula, now this is a bit involved. This is actually where all of the work is going to be. A with V1. Well, no, we're just looking for the image of V1. So here, right? All right. So So if you want to find this, so let's just work through this one. You multiply, so, well, no, because A, remember, A is in terms of bases B and B prime, right? So you would have to find the coefficient in terms of those vectors. All right, so V1, if you want to multiply it by A, V1 would actually have to be, it would have to be like this if you wanted to use that matrix. So you needed the coefficient in terms of the matrix B. Okay, so we have to be careful with that. Okay. 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 Excuse me. Okay, so now the next thing we want to look at is we want to find a formula that so we'd like to find a formula for this, right? Where we have x1, x2, x3, and x4. All right, now here is where all of our kind of all of the work is going to come into play, right? Now, what we want to do here is we would like to figure out, let's look at we're going to need so we're going to look at our standard bases. Yes, I will always use the standard because when they write it like this, it's not it's relative to the standard basis, so we want to just change it using our standard basis. Excuse me, our standard basis vectors. Okay, so then from here, what we would like to do is we like to look at, all right, so we look at our domain basis, the basis for R4. We have V1, V2, V3, and V4. All right, and then here we have our standard basis. Okay, so what we do from here is we would like to look at, so here's the process that we would do. We would look at E1, and then we would have, we would figure out we would have to figure out the this C1, C2, C3, and C4, right? And you would have to do this for each one of those, right? Which is why I said this is where a lot of the work is gonna happen here. So let me use a different variable: K1 V1 plus K2 V2 plus K3 V3 plus K4 V4. All right. Okay, and then you would do this over and over for E3, E4, and then E3. Where you would find these variables here, and then you would use the transformation. You would take these, again, I'm just kind of glossing over the details. I just want to get you guys on the right track, because this does take a lot of computation. So I would use something like this. I won't give you that like a 4x3. It'd probably be it would be a lot smaller on the exam. But this is what you would have to do, right? And then what you would do from there is you would take these column vectors. So you would take A. Once you find C1 through C4, you would take your matrix A and then multiply them by C1, C2, C3, C4, and then A times K1, K2, K3, K4. And so forth, right? Then this would be the new image. So, and then you would build a new matrix. Where these would be right, where the columns would just be A times those coefficients, or when you find the coefficients for C1, K1, and then for the other standard basis vectors. I used some kind of technology because I got through half of it, and the fractions do get a little, they get really involved. The numbers they're not nice, I guess is what I'm trying to say. Okay? All right, does that make sense? Kind of where I'm kind of pushing you in the right path here. Okay, yeah, use Octave Online, or if you don't have MATLAB. So that one is a bit, the calculations are a bit involved there. Okay, but at least I think we're on the right track there. Correct. Yeah, it'll be a matrix, a new matrix multiplication. But now notice here that your new matrix multiplication is not in terms of the basis B. It'll be in terms of the standard matrix. So you can just plug in x1, x2, x3, x4, and you don't have to change to the coefficients here anymore, because you're essentially undoing the change of basis. Okay, so that gets us through 11. Someone had a question on... Correct, yes. So once you have that, once you do part C, in part D, you just plug in 2, 2, 0 directly, and then just do the matrix multiplication. All right, so let's see. I have here... so homework, let's look at homework 10. Someone asked about number 5. Okay, so now here, this is just, they tell me that I define this transformation. T of P is equal to X of P prime. All right, so I have a transformation where we go from P2 reals into P3 of real numbers. All right, so real value polynomials. Okay, and for number 5, they just ask which of the following are in the null space. All right, now if I have a transformation defined like this, again, I'm looking for when does this happen, right? When do I take a polynomial P and then it gets mapped to the 0 vector? In this case, the 0 vector is just a 0 function. All right. Now, if we look at how I define this, so the way I define this is I take a polynomial P and I multiply it by X. So what that essentially does is that it raises it by a power, right? So you raise it by a new power. All right, well, if I want to get the 0 vector, the only way that's going to happen is if my polynomial starts off being the 0 vector. Because then it wouldn't matter when I do this transformation. It would always be X times 0. And that would give me the 0 vector. All right, and this is actually the only one that's going to work, right? Anything else, a constant polynomial, a linear polynomial, it would always get moved up by 1 degree. So if it's going to stay at the 0, it has to be, the only one that'll work would be 0. So in that case, for 5, the answer is B. Okay, does that clear that up for whoever asked that question? Okay, so if that's okay, I'm going to move on to homework 10. Someone asked about number 7, and then I'll jump back to homework 11. Okay, so for homework 10, number 7, so we're given a basis. All right, and I define a transformation within the same vector space. And they tell me it's linear. All right, they tell me it's a linear transformation, and they also tell me that this is a basis. Okay? All right, so based off of that, and also, so this is all the given information, right? The transformation of V1 is V1, transformation of V2 is V2, and so forth. So this is what I have, right? These are all the assumptions that I'm making. Okay, and what I would like to show is that T is the identity transformation. All right, or in other words, that this is true for all V in the vector space V. Okay? Now notice here that I only know what happens to the basis vectors, not for every single V. But that is okay, right? Remember when we talked about transformations, we said that it was enough to know what the transformation does to the basis vectors. Okay, because let's take a look at, so in this case, this is an exercise where we're going to use properties of linear transformation, right? So for example, I know that since V is in vector space V, I can write it as a linear combination of its basis vectors. I know that I can write it like that. right? This is just a property of a basis. It can be written as a linear combinations. Those coefficients, C sub 1 through n, they exist, right? All of them, they have a value that I can find if I knew what V looked like. Okay, so let's take a look at, so from there we would build our argument, right? We'd say, all right, take T of V and take T so you would write it like this, right? Substitution, and then using properties of linear transformations, you would have this. That will give you that, right? Using the properties of our linear transformations. And then from there, from our assumption, I know what these values are. This is just V1, that's V2, and then all the way to Cn Vn. All right, but this is just V. Right, so what did we just show? We just showed that for any vector, now notice here, now we've actually shown we have the identity, right? This is any vector V. The transformation of any vector V gives us back V. So we have our identity operation. Okay, any questions on that example? Okay. All right, let's see. So let's go back to homework 11 if there's no questions on this one. So homework 11, someone asked about, so we went over 6. Let's look at 8. Okay, so we have a transformation from P1 to P1. All right, and then the transformation is defined. Okay, so let's see here. They give us that. We have 2 bases. B is composed of this P1, P2, and B prime, that's Q1, Q2. Excuse me. All right, so let's look at, we want to create a matrix with let's look at matrix with respect to B. So let's look at the basis vectors in B, right? B. So again, the way we generate these, I'm going to do this, right? One thing that, to create my vectors, I'm going to look at column vectors where A0 and A1. All right, the constant coefficient and then the coefficient of the linear term. So let me see what happens in terms of here when I take the transformation of basis vector P1. All right, P1 is 6 plus 3x. Okay, so 6 plus 3x would be 6 plus 3 times x plus 1. So that gives me 6 plus 3x plus 3. So we get 9 plus 3x. All right, or in other words, if I'm going to think of this as a column vector, I'm going to think of it as 9, 3. All right. Okay. Then I'll look at what happens to the next basis vector. The next basis vector is 10 plus 2x. So here we'll have 10 plus 2x plus 1. So we would get 10 plus 2x plus 2. And we get 12 plus 2x. So in this case, we'll have 12 and 2. Okay, so now what I have here is I have here, all right, and T, this matrix is relative to that matrix B. Okay, so this, if I call this my matrix A, it's relative to that matrix B. So what I would like to find is I want to change my matrix to this B prime. So I want to find this matrix A prime where we have P inverse, and if I call that A, AP. Okay, so I would like to find it using this, this property here. All right. Okay, any questions so far? So now we need to find the change of basis. All right. So now let's take a look at so I'm going to take this, right? And if this is relative to my matrix B, what I would like to do next is let's look at the other basis vectors, right? Q1 is 2, and then Q2 is 3 plus 2x. Okay, so what I would like to do here is I'd like to find Q1 here. I'd like to find that in terms of so 2 in terms of C1 P1 plus C2 P2. Okay, so then from here, let's see, we have 2 is C1, P1 is, what is it, 6 plus 3x? And then C2, P2 is 10 plus 2x. All right, so here, we have something like this, and then just setting components equal to each other, we have 6 C1 plus 10 C2, that's equal to 2, and then we got 3 C1 plus 2 C2 is equal to 0. Okay, and then here, let me simplify this here. So C1 is equal to negative 2/3 C2. And then plugging that in here, we get 6 times negative 2/3 C2 is equal to 2. Okay, so we get C2 is equal to 1/3, which means C1 is negative 2/9. All right, so what that gives me is a way to start finding this matrix P, right? The transition matrix to my new basis would come from the coefficients here, negative 2/9 and 1/3. Okay, and then you would do the same thing with the other one, right? Again, for the interest of time, just to set it up here, and then after that, you'd find the inverse and do a matrix multiplication, right? So from here, what we would do next is you'd look at your Q2. Which was 3 plus 2x, and I would see all right, and I would solve that system, right? You distribute, you put together, you distribute here, and then you set the components equal to each other, and you solve the coefficients. Yeah, I think the question asked you to use the theorem where we had to find that transition matrix P. But of course, there's more than one way to do this, right? You can just do it. You can compute it directly if you want to find the transition matrix relative to B prime. All right, I think here it was more just an exercise in going from first to B and then to B prime and finding it that way. Okay, but yes, you can do it directly as well. That would be okay. All right. Okay. Let's see. So that's 8. So number 9. Someone asked about number 9. Okay, so in number 9, yes, there will be eigenvalues and eigenspaces will be part of the exam. Gersurun. Okay, so for number 9, we're told that A is similar to B. All right, so here, this is our assumption. And I would like to show that A squared is similar to B squared. Okay, so here is we need to show. Okay, so again, let's start with our assumption, right? So if we want to start our proof here, we'll start by this assumption. If A is similar to B, that means that okay. Okay, so if A is similar to B, that means that this has to be true, right? That there exists a invertible matrix P. Okay, so let's just go from there. So here, so let's start here and let's see if how we can use this here. So A squared is just A times A. Right, and now let me substitute here. Right, A all right, so here just substituting. All right, and then one thing that so now what we see here is again, right, all these are they're all square matrices, so all the operations are defined. So I can associate them however I want, right? And now I'm gonna associate these right here. Right, so P times P inverse is the identity matrix. All right, again, identity n by n, and again, associating this, B times the identity is just B. All right, and again, associating again, B times B can be rewritten as B squared. Okay, and now notice that, all right, this is all equal. So A squared is equal to P inverse B squared P, right? Or I know this is an invertible matrix. It's the same invertible matrix from A similar to B. So what that implies is that A squared is similar to B squared. Okay, any questions on this one? Are we okay with that? Tom, does that clear things up? Okay. All right, so let's do one of these eigenvalue ones. Let's do number 10 on homework 11. So here, let's see here. Okay, so we're given a matrix A. All right, and again, we want to find the characteristic equation. So the characteristic equation is the determinant of this operation. All right, so if we look at part A, so what we're after here is lambda minus 5, negative 2, 0, lambda plus 1, positive 8, 0, lambda plus 2. Okay, so we're after finding the determinant of this, and the determinant would be the characteristic equation. So again, let's expand here, I guess, along that first column here. So I'm going to look at lambda minus 5, and then the cofactor all right, and then that one's 0, so then minus 1. And then here, blocking this one out, we get negative 6, 8, lambda plus 1, negative 2. Okay, and then from here, we'll get lambda minus 5, lambda plus 1, lambda plus 2. And then out here, we'll have 48 minus plus 2. Okay. All right, I'm trying to see if I can factor this, but it doesn't look like I'm going to have to multiply this out and get a big kind of mess here. So let's see. So from here, we'd have 2 lambda, 3 lambda, 10. Okay, and here we get lambda cubed. Lambda squared, and then here minus 3 lambda squared, minus 3 lambda, minus 10 lambda, minus 10. Okay, so I'm playing kind of fast here, so I think that should be correct. So let's see. Now we got to find roots for this thing. So let's see. So for something like this, again, this coefficient is 1, so I'll start by guessing whatever factors of 36 are. But let me speed up my guessing here by kind of cheating a little bit. right. Okay. Minus 12 lambda. I got 15. Okay. All right. So, like I said, I'm going to speed up my guessing here. I would guess factors of here, but here, let me do that. Okay, and then here, 1, -4, -6. So that gives me positive 24. That gives me 9. And then that gives me negative 36. So we get 0. All right, so now we get lambda. So first of all, that's our characteristic equation. Okay, lambda, -4 is a root, so lambda plus 4, and then what's left is lambda squared minus 6 lambda plus 9, and this is factorable, so we get that. Okay, so we have part A, we have our characteristic equation. So now we find the eigenvalues, which are going to be -4 and 3. Okay, so then from there, that gives me, so we have part A, part B, part C, a basis for the eigenspace. So we're going to have two eigenvalues, so we're going to have two bases for one for each eigenvalue. All right, so now let's look at lambda equals to -4. Okay, and I think here we're going to go back to that equation here, right? So I'll plug in -4 here. Okay, and from here we'll do some we'll do row operations. One thing here, I'm just gonna flip these around, R2 and R3, or R1, excuse me. Okay. All right, and then now I'll use that as my pivot. So we'll multiply -9 R1, add it to R3, and that'll be my new R3. And then plus 18 minus 2, 16. Okay, and here once again, we'll have twice R -2 R2 plus R3, and that'll be my new R3. All right, so we would get something like this, and now it's in echelon form, which means here we have a free variable here. In this case, if we think of this from R3 to R3, here we'll think of x3 is my free variable. x3, I'll call it a t, which means we get negative 3x2, or x2 8/3 t. And from here we'll have negative x1 minus 2x3 equals to 0, or x1 equals to positive negative 2t. Okay, so that means that here our vector x, or the eigenvector, here would look something like negative 2 8/3 1t. So eigenvector would be any linear combination like or any linear combination here, or any multiple of this vector. So for our basis, we'll just choose the when t is 1. Again, if you wanted to know fractions, you could have chose t as 3 and then use that vector. But either way, it's the same thing. All right, and you would repeat this process just for the interest of time. I think you can repeat the process by letting lambda equal to 3. All right. Okay. Any other questions? Any last minute questions? I can maybe answer one or two quick ones. If not, I'll be on campus tomorrow, and I'll have normal office hours tomorrow and Tuesday. It should. Like I said, I think it does, but it's not guaranteed to. There are cases where it doesn't hold. Okay, so it should have to, but if it doesn't, it's not incorrect. All right. All right, guys. Good luck with your studying. I'll see you guys Tuesday or tomorrow. All right.